Okay. So last week we discussed the conservation laws, and this is a quick review. So we start with the Reynolds transport theorem. Which can be written in this way. Is equal to plus right? So here V is a material derivative, material volume. It's a volume of same fluid particles. So this means you are following a fluid particle, and look at the rate of change of this quantity. So you see how this quantity changes as you follow a fluid particle. And there are two components, two contributions. One is you just assume this material volume is fixed, and what happens in this F. Okay, that's what you see here. And this is the contribution from the flux through the boundary. So this is V of t, and this volume is surrounded by S of t. Okay. So the reason why we have two terms here is not only F depends on time, but also volume depends on time. That's why you have two contributions. So then this is a flux, and we looked at this quantity by taking a rectangular box, and the last time we looked at how we can evaluate this integral along this surface and this surface and this surface, right? And so let's say the center is located x, y, z, and then if this is delta x and this is delta y and this is delta z, then for example, on this surface, u dot n is nothing but u, because normal vector n is normal vector, which is away from the fluid. So this time, I'm interested in fluid inside of this rectangular box. So normal vector is away from the box, and therefore u dot n is nothing but u, because u is u v w, and n is 1 0 0. Right? So when you take an inner product, then you get u. So you have to evaluate at this f times u at x equal to x plus delta x divided by 2. Okay, that's the location of this phase. And so what you did is fu evaluated at x equal to x plus delta x over 2. That's what happens, what this guy is on this surface, multiplied by delta y delta z. That's the area of this phase, right? And then we take the difference between this guy and this guy, because normal vector is minus 1 on the other phase. So you have fu evaluate x minus delta x over 2, delta x delta y, or delta y delta z. So we did a Taylor expansion and so on. We end up with d dx f times u delta x delta y delta z. So this is a volume of this rectangular box. So at the end, what we have is this along, when you look at these two faces, then you get this. And if you look at the front face and the face on the back, then you will see f times v divided by y derivative of f times v. And if you look at top and bottom, then z derivative of f times w, right? So you sum up together. So the first, the conservation laws that we looked at is in conservation of mass. In this case, the F is nothing but density. Then density times volume should be mass. So the conservation of mass says, d dt rho dv has to be 0. This is a physical law, and therefore you can write the left-hand side as sum of this, and that has to be 0. And if you evaluate this guy and this guy for this rectangular box, then you end up with d rho dt from here, and then you end up with d dx rho u, which comes from here. And then you have to look at the other face, which is d dy rho v, and d dz rho w is equal to 0. Right? That's what we got, the equation from conservation of mass. And then I said that equation can be written in this way. So you expand this, and if you use vector form, this is what you end up with. And this one, I can rewrite this in terms of material derivative. Okay? And therefore incompressibility meaning that it's hard to compress, so you cannot change the volume easily. And so not only mass is conserved, but also the volume is conserved, and therefore density is conserved. For this case, we assume the density is equal to 0. The material derivative of density is equal to 0. So meaning that when you follow fluid particle, the density of fluid particle is always the same, meaning that the volume of fluid particle is the same, since mass has to be conserved all the time. So with this, then we end up with, we can split this one equation into two. So we have continuity equation like that. Okay. So this is the result of conservation of mass that we went through. And then we talked about conservation of momentum, linear momentum. So this time, when you follow fluid particles, if you look at the change of linear momentum, so momentum is mass times velocity. So you have density times volume, which is mass times the velocity. So you have a linear momentum. So for the linear momentum, instead of this guy is equal to 0, momentum can change. In other words, velocity can change if the fluid particle experiences a force. Okay, so if you apply force, then fluid particle can accelerate or decelerate. By doing so, velocity will be different. Therefore, linear momentum has been changed. So if you have force applied to the fluid, then momentum can be changed, and the force can be divided into two parts. One is body, and the other is surface. And F body is typically due to the gravitational acceleration. Right. So this is just weight of fluid. So here G is nothing but 0, 0 minus G if positive Z direction is obeyed. Okay? So far so good? Then the left-hand side of this, for this rectangular box, we can get the T rho U times delta X, delta Y, delta Z, which is a volume. So that's the first term that we get. So here F is rho times U. Okay. So this is F. So this is a local time derivative, first term. And the second term will give us d dx. So what do we get? Instead of just rho U there, I will get, over there F is rho. Here F is rho U vector times U. Okay? So previously I had the rho here. Now my F is rho times U, so I put this. Okay? So look at this guy and that guy. So I here I have rho here. I have over there I have rho times U. But this is vector because I have three linear momentum in the x, y, and z. So I have d dy rho u v and d dz rho u w. Okay? And therefore F body, also right hand side, is rho g delta x, delta y, delta z. Yeah, that's right. And then I did delta x, delta y, delta z. Oh, so I can erase this. So the next question is how we write the force, surface force. Okay, that's what we are going to talk about now. Okay, the surface force is due to contact between two different fluid particles. Okay, so if you have two fluid particles here, then there is a normal force which push because two fluid particles push to each other. Okay, that's a normal force, and the other is a tangential force, which is due to the relative motion. Okay, so if you look at the fluid rectangular box again. On this surface, there is a force due to the normal force in the normal direction, which we call sigma xx. Okay, and of course there is a force in y and z direction. Okay, so this is a sigma, let's call it xy, and this is called the sigma xz. So on this surface on the right hand side, there is a force normal to this surface, which I call sigma xx, and the force in the y direction due to the tangential motion in the relative motion in the y direction, and also there is a relative motion in z direction. So I have another force in the z direction. Okay, so x, y, z. The second subscript represents the direction, the force, direction of force, and the first subscript represents the normal direction of the surface. So in this case, normal direction is x direction. So that's why I put x here for the first subscript. And the second subscript, represents, direction of force. Of course, in each surface, you have 3 force components. Okay? So this is a stress. Instead of force, it's a stress, which is force divided by area. Okay? So what you need to do is compute, to compute a force, what you need to do is multiply stress by area. Okay, that's what you have to do. Not only on this surface, but also you have surface, force here in the x direction. So this time, I can call this sigma yx, and this is sigma zx, because the force direction is x direction, and normal direction on this surface is y, and here normal direction is z. So that's what how I give these names. Of course, there are other forces right here and here as well. But if you're interested in only x component, what I have to look at is this guy, this guy, this guy. Okay? So in the x direction, so surface force if I look at the x component, in terms of stress, what I need to do is sigma xx, evaluate x plus delta x divided by 2, y, z. This is stress, and then I have to multiply by area as before. So that's a x force here. And also I have to consider the other phase, and that will give you okay. So these are the 2 contributions from here and here, because stress in this direction is in the negative x direction. That's why I have a negative sign. And then I have to consider this guy, sigma yx on this surface, front face, and the face in the back, which gives sigma yx x y plus delta y divided by 2, and z, and delta x and delta z, and plus. So this is a sigma yx minus sigma yx x y minus delta y divided by 2, z delta x delta z. because this face is located at y plus delta y over 2, and the face on the back is located y minus delta y over 2. Finally, I have to look at top and bottom, and the force in the x component, which is sigma zx. I have xy z plus delta z divided by 2, delta x delta y. That's the area of the top surface, and minus sigma zx xy z minus delta z divided by 2, and delta x delta y. Do you know what I'm doing? I'm just, look at the force in the x component. On this surface, I have sigma xx. On the other surface, I have minus sigma xx. Okay? And also this surface and top surface, we have sigma yx and sigma zx. So once again, I can use, Taylor expansion, and then I end up with. So I have to take x derivative, and then I have to take a y derivative. You can do the Taylor expansion. The first order term is so this is a surface force in the x component. Then we can easily write the y component. So I need an x derivative, I need a y derivative, and z derivative. What do I have to put? Sigma xy. This subscript matches with this, and the second subscript matches in a direction. So I have a sigma xy, I have sigma yy, and sigma zy. Okay. And likewise, the z component is easy. So xz, yz, so those are the surface forces that we get. And also we can call this is f of x. No. F surface x delta v for shorthand notation. Okay. Delta v is delta x, delta y, delta z, and I call this is this. Okay. Just for shorthand notation. If I introduce tensor notation, it's easier to write, but this time I just going to use just vector notation later. So now what I need to do is just this one is equal to this plus all this, okay? And we have d rho dt equal to 0, and one solution is rho is constant, right? This doesn't mean this, okay? Rho can vary in space and time as long as the material derivative is equal to 0. But for this class we assume density is constant, okay? Almost constant, so we assume it's constant. And then we have a continuity equation. So I have three unknowns, u, v, w, and now we introduced how many unknowns? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 unknowns here, and I have 3 unknowns here, u, v, w. So I have 12 unknowns. I have only 4 equations. This is scalar equation and 3 vector equations. So I have too many unknowns. So what we need to do is have a closure, which gives the relationship between the stress and the velocities, which is basically the relationship between stress and strain. So that's what I'm going to talk about. So finally, the momentum equation is given by okay. So this is nothing but rho. No, sorry. No, I cannot write this right here yet. So what I end up with this. Rho uv plus rho uw, right, is equal to rho g, and then I have f surface. Okay. So x component of this is this guy, and y component is this. So this is fy component, and this guy is z component. So I dropped the volume, and then I end up with this. Okay. So next step is I'm going to write this f in terms of velocity. Okay, by doing so we'll get a Navier-Stokes equations. For Newtonian fluid, this is a fluid which has a linear relationship between stress and strain. The relationship between stress, which is a sigma, and strain deformation are given by the following. So this time, sigma xx is this guy. Sigma xx is given by pressure plus mu times 2 mu du dx. And sigma yx is given by minus p plus mu d u d. It doesn't quite matter, it's a symmetric, so but to be consistent, du dy. No, sorry, without p. So I have a sigma xx, sigma yx, sigma zx. And for Newtonian fluid, then we assume linear relationship between, this is a rate of strain deformation, okay? And linear relationship between stress and strain, basically. And the proportionality is called, mu, which we call, viscosity. Or it is related to stress. It's a dynamic viscosity. Okay. We often call it viscosity. When we say viscosity, typically, dynamic viscosity. Okay. So there is a linear relationship between stress and strain, and the proportionality is called, mu. And likewise, the sigma yx can be represented by strain like this. So here you have x, you have u, and you have y derivative, and then you flip, and this is the y component and x derivative. Okay, and so by noticing that, you can see this has to be symmetric. Okay, even though I switch, I end up with the same thing. So this is a property of fluid. So this, the relationship works for, most fluids that you are dealing with. Water, yes, okay. But if you have a different, fluid, then the relationship between stress and strain might be different. Okay. You can, toothpaste, for example, you can think, that toothpaste as a fluid, and then that toothpaste doesn't have, this linear relationship. It might have, non-linear relationship, okay? But, for water, this is a very good approximation, and then we represent, stress in terms of, velocity in this way. And likewise, y component, y is minus p plus 2 mu dv dy, and the sigma zz is minus p plus 2 mu dw dz. And the last thing that we need is sigma yz, which is mu dv dz plus dw dy, and which has to be the same as sigma zy. So we have 9 components for stress, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 1, 2, 3, 4, 5, 6, 7, 8, 9, okay? Everything is written in terms of U, V, W, and P, okay? So if you look at this guy, sigma xx is a normal force in the x direction, so this is a really normal force. One is due to the pressure, so they push each other, and also this is a force that you need to pull fluid particle. Okay, so if you look at the two position here and here, if the velocity are different, then you have to stretch. Okay, that's what the force that you need to stretch. And this is a force, for the relative motion. Okay, in this case, like this. That's what you need. And this is a relative motion. So in this case, top and bottom and in this way. Okay, that's the force that you need. And there is a resistance. So you are trying to, for example, in this case, you are trying to pull in the x direction, and the fluid resists to that pulling, and that resistance is coefficient for the resistance is called mu, which is we call viscosity. So if there is no viscosity, then you don't need any force because there is no resistance. Okay, because the fluid has a viscosity, and that's why you have to apply force to stretch. If you don't have viscosity, you don't need this force. Viscosity is kind of stickiness of a fluid. So sticky fluid, like a corn syrup, for example, is a very viscous fluid, and water is very viscid fluid. Okay, so the next step is you plug in this relationship. So fluid that has a linear relationship we call Newtonian fluid. If fluid don't have the linear relationship between stress and strain, then we call non-Newtonian fluids. And the next step is we substitute all these expressions here and then find small fx, s, and so on. And so when we plug in this into here, then we end up with what? d dx minus p plus 2 mu, right? That's a d dx, d sigma xx dx. And then we have a d dy 2 mu d u dy plus dv dx, and then we have d dz 2 mu du dz plus dw dx. So I'm looking at this x component, and then I end up with minus dp dx plus mu du dx. Second derivative of u. Okay, I have first derivative and I take another derivative. And only I just took one of them. And then I look at this guy. I have d squared u dy squared plus I'm looking at this guy. Oh, sorry, I need a mu here instead of 2 mu. And then I end up with okay. And then the other term is I pull out d dx, and then I end up with a du dx. So I had a 2 here. I split into 2, 1, 2. And then I'm looking at this guy. I already include this part here. I'm looking at this guy. I change the order of derivative, and I pull out the x derivative. I end up with dv dy. And I'm looking at this guy, and I pull out x derivative, and I end up with this. Okay? What is this? Continuity equation, which is 0. So this is nothing but divergence-free condition. So this guy goes away. Okay? So what you end up with, dp dx plus mu times Laplacian of u. So x component is minus dp dx plus mu Laplacian of u, where Laplacian is second derivative with respect to y plus second derivative with respect to z, and so on. Okay? So now we can write, the surface force in a vector form, which is minus grad p plus mu so y component will be dp dy, z component will be dp dz. So in a vector form, I can write as a gradient. And here I have to change u to v for y component. For z component, I have to change u to w. That's why I wrote this way. So this is the final representation for a surface force. So finally, when you plug in this to here, and I have to plug in here, and then I rewrite it, and then I end up with the and I have grad p plus mu in fact, this one I can rewrite as rho that's what I wrote over there plus okay. You have to go through, and this guy is nothing but 0 because this is the equation from conservation of mass. So that's why I wrote only this part here. Okay. So our governing equations are this plus this is equal to 0. These are the governing equations for us. So this equation, the three equations here, is called the Navier-Stokes equation. So unknowns, u, velocity vector u, and pressure p. And we have 4 equations for 4 unknowns. Okay? And physical parameters are mu, rho, and g, gravitational acceleration. So once you fix in a fluid, your density and viscosity are fixed. and rho, then gravity is always 9.81 meter per sec squared on the Earth, so it doesn't change. And then all you have to do is solve for U and P. And for water, mu is one. It depends on the temperature, but this is a 20 degrees Celsius. The dynamic viscosity is given by this. And rho is right. So once you fix in a fluid, and then you fix the dynamic viscosity and density, and for air, mu is 1.8 times 10 to the minus fifth. And density is about 1. So dynamic viscosity of water is much greater than dynamic viscosity of air. So that's why it's harder to pull the object in water than in the air. Okay? Because stress is larger. For given strain, the stress is larger because stress and strain has a linear relationship. The proportionality is nothing but the viscosity. So when viscosity is larger, then then the stress is larger. Therefore, the drag force to pull the object or body is larger. Okay. So, for example, frictional drag is greater in water than in the air for the same object. And there is another viscosity called kinematic viscosity, which is called nu and defined by rho divided by mu, and this time this is about 10 to the minus 6, and for air nu is roughly the same as dynamic viscosity, and the unit of this guy is meters squared per second. So dimension of kinematic viscosity is L squared divided by T, because it's meters squared divided by second. So that has to be the dimension. So kinematic viscosity is pretty small, but it's not exactly 0. So that's why we have to include a viscosity in some discussion, and sometimes we can neglect viscosity. We'll talk about that a little later in detail. Okay. So far we have derived the governing equations, Navier-Stokes equations, and continuity equation. If you don't follow all the details, that's okay. But I hope you to look at your notes and to go through at least one time. And the important thing is this is a mass times acceleration basically. So the rate of change of linear momentum is balanced by the body force and the surface force. And surface force has two components. One is the normal stress, and the other is tangential stress. Okay, so normal stress is either due to pressure the resistance to the stretching, and the tangential stress is resistance due to the relative motion. Okay, fluid resists to the deformation, so you have to apply force to overcome that resistance. So that's why you have those. And this is from conservation of mass, and this is a very special form from the conservation of mass, because we assume fluid is incompressible and it's hard to compress, hard to change the volume. That's why we have this. And here we assume density is constant, but if you include defective density variation, then you have to solve d rho dt equal to 0 as well. And one more thing is this part, inside of parentheses, this is a material derivative of velocity. That's why this is acceleration, mass times acceleration. Okay? So from now on, all we have to do is solve this system. Okay? So today, I'm going to show you a example for which I can find the exact solution. Okay? In other words, I can solve this system of equations. There are not many examples for which you can solve the system. This is one of them. So the problem that we are interested in is the following. We have an inclined plane, and then you have a flow over inclined plane. Okay, and this is a free surface, so you have a plate, and you're just there's a flow with a constant depth h. Probably you have seen such an example in reality many times. And to make the problem simple, we assume d dt is equal to 0. The partial time derivative is 0 no matter what we have here, meaning that the flow is steady, as we discussed. Okay? So fluid particles move, but it's steady, meaning that you see the same shape and the velocity every time. That's what steady means. Okay? And then, in addition to that, let me put my coordinate system like this. And z is perpendicular to my plate. Okay? And let's say this angle is theta. And also we assume the flow is two-dimensional. I'm making a lot of assumptions, okay? Meaning that the flow doesn't depend on y direction. So in other words, d dy of anything is equal to 0. In addition to that, I'm making the flow is unidirectional. So this means v is 0. Okay? So this means this, and this means this. Okay? So I have only the x component, flow is going this direction, but there is no flow in the y direction. What happens if I have the flow in the y direction? Then free surface will move. Okay, so to avoid that, I assume flow is only in the x direction. So flow is going that way, then free surface will be changed, right? And so then problem is much more complicated. So to make the problem as simple as possible, I assume flow is unidirectional. Okay, so with this, my continuity equation is du dx plus dv dz dw dz. I didn't write dv dy, right? Because v is 0. And sorry, this has to be w. Sorry, has to be w. So there is no vertical velocity. So w is 0. This guy is 0, meaning that du dx is 0. So u can depend on x, z, and t, and it's independent of time, independent of x. So u has to be only a function of z. That's what it means. So if you look at the vertical velocity profile, it will change in z like this. We'll find the solution, but it looks like this. Okay, it will only depend on z. So that's what we got. And then we have to write this equation in the x component, because v is 0 and w is 0. It's unidirectional. So all I have to do is write the x component of the Navier-Stokes equation. So I have du dt plus u du dx plus w du dz is equal to minus dp dx. No. Rho g x component plus minus dp dx plus mu right? And let me write down the w equation as well. Most terms are 0, right? These are all 0 because w is 0. These are 0 because w are 0. W is 0. This guy is 0 because it's steady. This guy is 0 because du dx is 0. That's what this continuity equation says. And this guy is 0 because w is 0. So the left-hand side is gone. This guy is 0 because u is independent of x. U only depends on z. That's what we got. So we don't have many terms left. So the only unknown is u and p this time. And I can find p from here. So my dp dz is equal to rho g z component. So gravity is acting downward. So there is a two component. So this is G, and this is Gx, and this is Gz. I think this is theta. Because this guy is theta, and no. This one and this one is theta, right? So therefore this is theta. So Gz component is minus rho G cosine theta. And x component is G sine theta. Rho is constant, as I said, G is constant, angle is fixed, and therefore P is minus rho G Z rho G cosine theta times Z plus some constant like this, okay? Now, when you solve, the partial differential equations, or partial differential equations, you have to impose, boundary conditions, and those boundary conditions will determine, a known constant, like C, okay? At this moment, the boundary condition here at the free surface for the pressure P is P equal to 0, okay? I will talk about, boundary conditions, much later for the free surface. And what you should, remember now is, on the free surface, the stress has to be 0, okay, stress free. In other words, when you have a free surface, if you apply stress, what happens? Free surface will move, okay? So to avoid that, what you need to do is, stress has to be 0. That's the boundary condition. And in other words, here, normal stress P has to be 0. So from the boundary condition, at Z equal to 0, which is P is equal to 0 at Z equal to 0, what we end up with is what? C has to be 0. Okay, so this gives you C is equal to 0.
C can be a function of x.
C can be a function of x. But it doesn't quite matter because, when I put Z equal to 0, no matter what dependence I have, that has to be 0. Otherwise, my boundary condition wouldn't be satisfied. Okay. So C has to be, this guy, no matter what, has to be 0. Okay? So here, another assumption is the free surface is flat. That's what we assume. Okay. So that's why we can apply, this boundary condition. And now we have a P, expression for P, and then we can get the x derivative, which is constant, 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 and only z here. So dp dx is identically 0. So what I end up is the following. So rho plus rho g sine theta, which is gx, right? So here gx is g sine theta, and then minus dp dx is 0, and then I have mu okay. So at this time I can integrate twice. This is constant, so I divide by mu, and then I have du, the here is minus rho g divided by mu sine theta, and integrate once. Plus constant, let me call C1. And then I integrate twice to get u. Okay. So I have to determine, C1 and C2. These are unknowns, integrating constant. Once again, we have to impose, boundary conditions. So boundary conditions for u is the following. So we have to impose boundary condition here and here. This is on the rigid boundary, and we have to impose boundary condition on the free surface as well. And at z equal to minus h, u has to be 0. Okay, that's a no-slip boundary condition. So this is always true. So this is called the no-slip boundary condition. At z equal to minus h. Okay. So he says, a fluid particle has to, stay on the rigid boundary, and there is no slip between, the fluid and the boundary. Since boundary is fixed, fluid has to be fixed. It has to be stationary. Okay. And if boundary is moving, then fluid particle has to move with the boundary. That's why we call no-slip boundary condition. Okay. So on the rigid boundary, you always impose no-slip boundary conditions for the velocities. And also at the free surface, we have sigma zx, which is mu du dz plus dw dx, right? As I said, stress has to be 0, and this guy is 0, and meaning that du dz has to be 0 at the free surface. So this is no stress condition, which comes from here. So this is a surface. We are looking at this free surface, and the stress in this direction is given by this, because the normal vector is the z direction, and the force in the x direction, the force direction is the x direction. So that's why we are looking at sigma zx and the W is 0, so all we have is this guy, and this guy has to be 0 at z equal to 0, meaning that du dz has to be 0. So you plug in this boundary condition here, and what do you get? So z equal to 0, I have to, so from here, z equal to 0, this guy has to be 0, meaning that this guy is 0 from here. And then I have to substitute this boundary condition to get C2. So U minus H is equal to 0, and therefore rho G 2 mu sine theta H squared plus C2 has to be 0. Am I right? And therefore U of Z is given by rho G 2 mu sine theta Z squared minus H squared. And P of Z is given by minus rho G Z, rho G cosine theta. So what it says here is when you have a flow on an inclined plane and you have a parabolic velocity profile like this. Okay? So this is U of Z. And the pressure increases. Z is a negative, okay? My coordinate system is here. So pressure, Z is always negative, and pressure is always positive as it has to, and linearly increases in Z. Okay? And the velocity is parabolic like this. So U is 0 here, as the boundary condition says, and also du dz, the slope has to be 0 here. Now, so we solved this set of equations, Navier-Stokes equation and continuity equation, for a very simple example. To solve this system, we have imposed a number of assumptions. We said the flow is steady, which is a big assumption. In reality, flow cannot be really steady. It always depends on time. And also we said flow is unidirectional. We have only U components. Cannot be true in most of cases. For example, if you have a little bumpy bottom, then the free surface wouldn't be flat. Okay, and then you have not only X component, you also have a Z component velocity as well. So that assumption might not be true. And what else? Also, it's not two-dimensional. There is always three-dimensionality in reality. So if you don't make such assumptions, it's not easy to solve this system of equations, or it's almost impossible to solve this set of equations analytically. Okay, so we have to rely on either experiments or numerical computations. Okay, and the but there are too many, the parameters involved, so it is not easy to do, experiments or computations for all, those parameters. So next time, I'm going to explain how you reduce, number of, experiments or computations to avoid, infinite number of, experiments or computations by using dimensional analysis. Okay. So on Thursday, I'm going to talk about, dimensional analysis and discuss a little bit more about, the Navier-Stokes equations. Okay. Any questions?
When you talk about Newtonian fluid, do you assume that fluid is incompressible or is it just different?
Those are the two different things. So incompressibility and the assumption of Newtonian fluids are independent. Okay. So even though flow is incompressible, fluid can be Newtonian or non-Newtonian. And even though the fluid is Newtonian fluid can be compressible or incompressible. Air and water, they are all Newtonian fluids. Okay. And this relationship between stress and strain is based on observation. Okay. So that's why Navier and Stokes get credit. Okay. Because they found those such a relationship, and then they use those relationships to write the equations. Okay. Any other questions? Okay.